what if I told you there was a single, elegant blueprint that could solve some of the most mind-bending puzzles in computer science? From Sudoku to finding your way out of a maze. It turns out one core idea can turn absolute chaos into a smart, manageable search. Today, we're going to unlock that master key. It's called backtracking.
So when you get right down to it, a ton of computational problems are really just about searching. But we're not just looking for anything. We're trying to find one specific, correct answer hidden among billions or even trillions of wrong ones. So how on earth do you find it without getting completely lost?
All right, let's make this real with a classic problem, the n-queens puzzle. The goal is simple. Place 8 queens on this 8x8 board. But here's the catch. No 2 queens can threaten each other. That means no 2 can be in the same row, column, or diagonal. It sounds straightforward, right? But the number of ways you could place them is just staggering.
And when I say staggering, I mean it. We're talking about over 4 billion possible ways to place those queens. And you know how many of those are actual solutions? Just 92. Can you imagine trying to check every single possibility? It's not just impractical, it's basically impossible. Brute force is a total non-starter. We've got to be smarter.
And that smarter way? That's the backtracking blueprint. Now, this isn't some complex, rigid algorithm. Think of it more like a powerful technique, a recipe for building a solution one step at a time, and crucially, knowing when to ditch a path that's going nowhere.
So here's the big idea. Backtracking dives deep down one potential path. It keeps adding pieces to the puzzle, step by step. But the moment it makes a move that breaks the rules, hits a dead end, it doesn't just give up. It just takes a step back. It undoes that last move and then tries the next option from that same spot.
Honestly, the maze analogy is perfect. Imagine you're walking through a maze. At every fork in the road, you make a choice. If you hit a dead end, you don't teleport back to the start, right? Of course not. You just walk back to the last intersection and try a different path. That's backtracking in a nutshell. It's a controlled, systematic retreat.
And this whole process boils down to a really simple 3-step mantra. Choose, explore, and undo. That's it. First, you make a choice. You place a queen. You pick a number. Second, you explore the consequences of that choice, usually with recursion. And third, if that path turns out to be a dead end, you undo the choice. You just wipe the slate clean and get ready to try the next thing. This little loop is the engine that drives every single backtracking algorithm.
Okay, so now that we've got the blueprint, let's see just how flexible this thing really is. Because it's not just for board games. This is a template you can stamp onto a whole bunch of different problems.
You see this pattern everywhere. Need to generate all possible subsets for permutations? That's just backtracking. You choose an element, explore what happens with it, then undo and explore what happens without it. Solving a Sudoku? Classic backtracking. You choose a number for a cell, explore if that works, and if it doesn't, you undo it. Even finding a word in one of those word search grids is just exploring different paths of letters and backtracking when the path doesn't spell your word.
All right, let's get back to our queens. We'll follow the blueprint. Step 1, make a choice. We'll place a queen in the very first spot, top left corner. So far, so good. No rules broken yet. Now we explore. Let's move to the second row and try to place our second queen. We try the first available spot, and whoops, that's not going to work. That new spot is on the same diagonal as our first queen, so it's under attack. We've hit a wall in our maze. So what do? We hit the most important part of the loop, undo. The algorithm backtracks. It literally just plucks that second queen right off the board, completely erasing that bad decision.
And now, right from where we were, we explore again. We try a different path. We place that second queen in the next spot in the row that isn't under attack. And the cycle just keeps going. Choose, explore, undo. Over and over until a full, valid solution is found.
Okay, so understanding the theory is great, but let's talk about how you actually put this to work. What do you need to know for a coding interview or just for tackling these problems in the real world?
So the elephant in the room with backtracking is always performance. And yeah, the time complexity can look pretty scary. It's often exponential. But here's the secret sauce. That undo step is actually a super powerful way to prune the search space. Every single time we backtrack, we're not just fixing one mistake, we're cutting off an entire branch of the decision tree, which could contain millions or billions of future bad choices. That's what makes these massive problems solvable at all.
Now, a common question is, wait, isn't this just like dynamic programming? And the answer is, no, not really. Think of it this way. Backtracking is like a marathon runner, systematically exploring every valid path to find all possible solutions. Dynamic programming, on the other hand, is a sprinter. It uses memoization to find the single best solution as fast as it possibly can. They're both incredibly powerful, but they're running completely different races.
So, if you're in an interview, here are your go-to talking points. Always start with the choose, explore, undo mantra. It shows you get the core concept. Then, talk about the state you need to keep track of in your recursion. Make sure to explicitly mention pruning. That's key to showing you're thinking about efficiency. And hey, if you really want to impress, for a puzzle like Sudoku, you can bring up heuristics like MRV, which is basically a fancy way of saying tackle the easiest parts first.
So if you walk away with just one thing, let it be this. The real power of backtracking isn't just mindlessly wandering through a maze. It's about applying that simple choose, explore, undo template, being super aggressive about pruning paths you know are wrong, and being clever about the order in which you make your choices.
Backtracking is an amazing tool for finding perfect, exact solutions. But it does leave us with a pretty fascinating question. What do you do when the problem is so ridiculously huge that even this smart approach is too slow? Well, that's when you start stepping into the world of approximation algorithms and advanced heuristics. But that is a story for another day.